Hi, Stu Schwartz from MasterMathMentor.com. This is video AB41. The topic is exponential growth and decay, and it covers the AB manual pages 232 and 233. In this video, we are going to examine a statement that we see regularly in calculus. The rate of change of some quantity is directly proportional to its current value. This means that how fast some quantity grows is a function of how large it is at that time. Here are some examples. The more money you have, the faster it will grow. The more you scratch an insect bite, the worse it will get. The more addicted someone is to a substance, the worse the addiction gets. And the more people with an infectious disease like COVID, the faster it will spread. We will see that these are all examples of exponential growth. So let's break down this statement. The rate of change of some quantity is directly proportional to its current value. We will call the quantity P, usually standing for population, although it does not have to represent people. The rate of change of P is simply the derivative, dP dt. And is proportional means some constant K times. So the rate of change of P is proportional to P can be translated dP dt is equal to Kp. That we know is a differential equation and it is separable. So we know that the rate of change of some quantity is directly proportional to its current value, can be translated as dP dt equals Kp, a separable differential equation. We separate and get dP over P is equal to K dt, and now we can integrate both sides. So we get the natural log of the absolute value of P is equal to Kt plus C. And solving for P, we write P as e to the Kt plus C, or P is equal to e to the Kt times e to the C. And again, we know e to the C is simply a constant. So P equals C e to the Kt. And usually we will write that as P is equal to P0 e to the Kt, because when T is equal to 0, P is equal to C. So we call the constant C P0, the population at time 0. So the statement, the rate of change of some quantity P is directly proportional to P, can be translated to the differential equation dP dt equals Kp, which we have just shown has the solution P equals C e to the Kt, or P equals P0 e to the Kt. You need to memorize that. So when K is greater than 0, that means that P is growing exponentially, and we can see the exponential growth curve emanating from dP dt equals Kp, which translates to P equals P0 e to the Kt, K greater than 0. And when K is less than 0, P is decaying exponentially, as shown by the red curve. It is based upon the differential equation dP dt equals Kp, which again is P equals P0 e to the Kt, but now K is less than 0. The problems in this video are all based upon the differential equation that signals exponential growth. Number 1 reads, when driving, you run over a nail. As the air leaks out of the tire, The rate of change of air pressure in pounds per square inch, psi, inside the tire is directly proportional to the current pressure. So at the time of the puncture, the pressure is high, so air escapes quickly. As time goes on, there is less air in the tire, so air escapes less quickly. In Part A, we are told that the tire pressure is 45 psi and decreasing at 0.036 psi per minute. We want to write the DEQ and then solve for y. Since the rate of change of air pressure in pounds per square inch is directly proportional to the current pressure, we know that dp dt is equal to kp. We know that dp dt is decreasing, therefore it is negative and 0.36. We know that p at time equals 0 is 45. So we have the equation negative 0.36 is equal to 45k, giving k equals negative 0.008. And therefore, we can immediately write our expression for the pressure within the tire at the top from the time of the puncture. P is equal to 45e to the negative 0.008 t. Part B asks what will the pressure be 10 minutes after the tire was punctured. So therefore we simply plug in 10 into our equation and we get P equals 45e to the negative 0.008 times 10, which is 41.540 psi. This tells us that this is a very, very slow leak. Part C reads, the car is safe to drive as long as the pressure is 20 psi or greater. How long is the car safe to drive? If the graphing calculator is allowed on this problem, then it's easy. We simply graph our two equations, P equals 45e to the negative 0.008 t, and P equals 20. Of course, we use x's, and therefore y equals 45e to the negative 0.008x, and y is equal to 20. We find the intersection point, which is 110.366, 20. That means that the car is safe to drive for the first 110.366 minutes. If your answer has to be justified, then the graph is not allowed. So we can do this algebraically, setting 20 equal to 45e to the negative 0.008 t. Dividing both sides by 45, we get 20 over 45 equals e to the negative 0.008 t, and therefore t is equal to the natural log of 20 over 45 divided by negative 0.008. We need to use our calculator to calculate this answer, and we get the same answer, 101.366 minutes. Notice throughout this entire problem, we never really used calculus. The calculus was used in Part A to go from dp dt equals kp to p equals p0e to the kt. We've already done that work. We do not need to show the calculus again. Number 3 reads, bacteria in a lab culture grows in such a way that the instantaneous rate of change of bacteria is directly proportional to the number of bacteria present. Suppose there are 3 million bacteria initially, and 3 hours later, that number has doubled. We are first asked to write and then solve the differential equation that describes the relationship. We have the magic words in the problem. The instantaneous rate of change of bacteria is directly proportional to the number of bacteria present. So that gives a differential equation dp dt equals kp. And we know that that is p equals p0 e to the kt. The calculus is in that step. From there, we can say that p is equal to 3 e to the kt, as p0 is equal to 3. We then will use the fact that in 3 hours there are 6 million bacteria. So we have 6 is equal to 3e to the 3k. Dividing out by 3, we get 2 is equal to e to the 3k. And therefore k is equal to the natural log of 2 divided by 3, or 0.231. So our solution to the differential equation is p is equal to 3e to the 0.231 t. You have all encountered this type of problem in pre-calculus, and when asked, the formula was the much simpler and elegant p is equal to 3 times 2 raised to the t over 3 power. What happened? First, realize that the formula for growth in pre-calculus was just given to you rather than generated mathematically as we did through calculus and differential equations. Second, realize that the two answers are equivalent. Since e to the 3k is equal to 2, then p is equal to 3 times e to the 3k raised to the t over 3. The 3's cancel, and we're simply left with 3e to the kt. The advantage of having answers in terms of e is because of their ease in taking first and second derivatives. And we will continue to leave our answers in terms of e. Part B asks, what will the bacteria population be 1 full day after the first measurement? We simply plug in 24 into our equation and get p equals 3e to the 0.231 times 24. Since 0.231 is an approximation, we will get an answer of approximately 768 million. If we use the more elegant 3 times 2 raised to the t over 3, we would get exactly 768 million. Part C asks, how long will it take for the population to grow from 1 to 2 billion? This is easy. The answer is 3 hours. Because it is doubling, and it takes 3 hours to double. It doesn't matter from what number to what number, as long as those two numbers are a double of each other, then it will always take 3 hours. Part D asks, why isn't the world inundated with bacteria? And the answer is simple. Exponential growth cannot continue forever. With bacteria, the more there are, the less food there is, the less room they have, and they will begin to die off. This is generally true in any type of exponential growth. There will always be a point where it will begin to level off, and we will study that more in depth in BC calculus. Number 3 reads, a manufacturing company determined that once it started a new TV advertising campaign, its monthly change of sales was proportional to the current monthly sales. In January, it sold 5,000 units, and in April, it sold 7,000 units. Part A reads, write and solve the differential equation that describes the relationship. We have the magic words, monthly change of sales was proportional to the current monthly sales. We normally would set January to be month 1, but it is convenient to think of it as month 0. And if we do so, then April will be month 3. So our differential equation is ds dt is equal to ks, meaning that s is equal to s0 e to the kt. And since we know that when t equals 0, s is equal to 5, we'll say that s is equal to 5e to the kt. We will now use the fact that in April we sold 7,000 units. So when t equals 3, s is equal to 7. So 7 is equal to 5e to the 3k. Dividing both sides by 5, we get 1.4 equals e to the 3k, and k is equal to the natural log of 1.4 divided by 3, which is 0.1122. So the solution to our differential equation is p equals 5e to the 0.1122t. Part B asks, how long will it take for sales to go from 10,000 units to 15,000 units? If we are allowed to do so, we can easily do this on the calculator. If not, we can do it algebraically as well. To do it on the calculator, we just graph y equals 5e to the 0.1122x, and at the same time graph y equals 10, y equals 15. We find the intersection of the blue curve and the red curves, finding that it reaches 10 in 6.18 months and reaches 15 in 9.795 months. So the difference is 3.6 months to go from 10,000 units to 15,000 units. To do the problem analytically, we first set 10 equal to 5e to the 0.1122t, divide both sides by 5, and get t is equal to the natural log of 2 over 0.1122, and that is 6.18 months to hit 10,000. We do the same thing, setting 5e to the 0.1122t equal to 15, and therefore t is equal to the natural log of 3 over 0.1122, which is 9.795 months to hit 15,000 units. Therefore, it takes 3.6 months to go from 10,000 units to 15,000 units. Carbon dating is a method that provides objective age estimates for carbon-based materials that originated from living organisms. Knowing how fast the element carbon-14 decays in terms of half-life, the amount of time for the element to halve in size, archaeologists can date the age of bones and fossils very precisely. The concept of half-life is very important in the world of nuclear power. Problem 4 deals with half-life. Radioactive decay is measured in terms of half-life, the number of years for half the atoms in radioactive material to decay. The rate at which radioactive material decays is proportional to the amount present. If 8 grams of the plutonium isotope, Pu-239, was released in the Chernobyl nuclear accident, how long would it take to decay to 1 gram if Pu-239 has a half-life of 24,360 years? Let R be the amount of the radioactive plutonium Pu-239. We say the magic words in the problem. The rate at which the radioactive material decays is proportional to the amount present, and that signals dr dt equals kr, or r is equal to r0 e to the kt, and we know that r0 is equal to 8. So our solution to the DEQ is r is equal to 8e to the kt. We need to find k. We utilize the fact that in 24,360 years, the 8 grams will be reduced to 4 grams. So 4 equals 8e to the 24,360k. Dividing both sides by 8, we get 0.5 is equal to e raised to the 24,360k. Therefore, k is equal to the natural log of 0.5 over 24,360, which is negative 0.00002845. When you do this on the calculator, I suggest that you store your answer, because just a small difference in the accuracy can make a big difference in our answer. So the solution to our differential equation is P equals 8e to the negative 0.00002845t. To find out how long it would take our plutonium to decay to 1 gram, we could either do it graphically or analytically. Graphically, we simply graph the equation and also graph y is equal to 1 and find out where they intersect. Analytically, we set 1 equal to 8e to the negative 0.00002845t, divide both sides by 8, and we get 1/8 is equal to e to the negative 0.00002845t, and therefore we are now going to solve for t. And t is equal to the natural log of 1/8 over negative 0.00002845, and we get 73,080 years. The Chernobyl nuclear accident occurred in the year 1986. Because of the very slow half-life of plutonium, Pu-239, it is estimated that the area around Chernobyl will not be safe for habitation for 22,000 years. Not all graphs based on differential equations give exponential functions. A slight change in the differential equation can radically change the modeling equation. For instance, this slope field and particular solution models the number of fish in a lake over time. Note that it is not exponential. We will examine this and other growth curves in video 42.